Hey guys, welcome back to chapter 8. What we're going to talk about today is different types of solutes being dissolved in solution and then how that changes the properties of that particular solution. So again, we've got our definition of a solution, so homogeneous or homogeneous mixture of two or more substances. The two or more substances that are dissolved are solvent, greater proportion, solute, lesser proportion. And what we're going to do is break down this idea of a solute today. So what happens if I put an ionic compound into solution? And what happens if I put a molecular compound into solution? How is that different or the same? And how does that affect the properties? So just to remind ourselves what an ionic and a molecular compound looks like. So ionic compound is a metal bound to a non-metal. And when a metal binds to a non-metal, what happens? There's a transfer of electrons. So we get two charged particles that are attracted to one another, that electrostatic attraction that's holding those charged particles together. A molecular compound is just another fancy name for a covalent compound. So molecular compound would be a non-metal bound to a non-metal. And we know when two non-metals covalently bond together that they will share electrons. All right, so let's think of some examples of solute particles that dissolve in water. So let's think about dissolving salt, like table salt, sodium chloride. And let's think about dissolving sugar in water. Okay? So table salt, sodium chloride, does it dissolve in water? So if I dump a little sodium chloride into some water, does it dissolve? Yeah, it does, right? It disappears. We don't see it anymore. And then sugar. So if I take a packet of sugar and I dump a little bit into water and stir, does it dissolve in water? Yeah, it dissolves in water, right? Sweet tea, that sugar dissolves, right? So those are two examples of compounds that dissolve in water. But they're examples of one being ionic and one being molecular. So let's take a look at what's going on. All right, so sugar in water. So does sugar dissolve in water? Well, yes, absolutely it dissolves in water. Well, how does it dissolve in water? For molecular compounds, all molecular compounds, when they dissolve or if they dissolve in water, they stay together as one big molecule. So the fancy way for us to say that is they do not dissociate. So when I put a sugar molecule into water, so this big honking thing here is a sugar molecule made up of carbons and oxygens and hydrogens. So when I put this big honking sugar molecule into water, there are some interactions between the water and the sugar that happen. So that's how it dissolves. But this big molecule stays together. It doesn't break apart or fracture into little pieces. So what we say is it does not dissociate or does not break apart. Okay. These interactions that cause it to dissolve are interactions that we'll talk about in chapter 11. What about ionic? So ionic, salt in water. Does salt dissolve in water? Well, yeah, of course it does. When ionic compounds dissolve in water, or if ionic compounds dissolve in water, they will do so by dissociating. So ionic compounds dissociate in water. Dissociate, again, is just a fancy word for break apart. So what we see here is we've got our purple and green sodium chloride molecule here, okay? So the green is the negatively charged chlorine, the purple is the positively charged sodium. So what happens is water wiggles its way in between these sodium and chlorine ions, and it kind of plucks them aside, okay? So what happens is a sodium particle will dissociate or break apart from this big one, and it'll be surrounded by water. Then a chlorine particle will dissociate or break apart from the big one, and it'll be surrounded by water. And so this happens all throughout the solution. So when ionic compounds dissolve in solution, they do so by dissociating, breaking apart, and we have lots of ions, charged particles that are floating around that water. As opposed to molecular, we've got this big honking neutral molecule. Okay. So that's the difference between molecular and ionic. Well, what's the difference? How does that change the properties of that solution? So let's look at an experiment, a very common one. So this is our light bulb experiment. So let me just break down this experiment really quickly. And I'm actually going to let me zoom in. No, not going to let me zoom in. All right, so I'm going to kind of break down this picture right here. So here we've got our beaker, and in this beaker we've got some sort of solution. Okay, we'll talk about what kind it is in just a minute. So we've got some sort of solution in here. Then I see two black rods. Those black rods are electrodes, so they conduct electricity. So we've got a wire coming into our solution, so attached to that electrode. And then this electrode, we've got a wire coming out of solution and attached to a light bulb. So this solution, if it conducts electricity, the electricity would come in on this electrode, travel across the solution, go out to this electrode, and light our light bulbs. That's what we see here. If our solution does not conduct electricity, we would have our electrical current come in this electrode and then just stop. It wouldn't have anywhere to go. It wouldn't be able to jump across this other electrode. So if the electrical current comes in and just stops, this light bulb will remain unlit, like we see in this first picture. So this would be not conducting electricity. This would be, it conducts an electricity. Okay. So let's look at this first one. This first solution would be an example of a molecular compound. So if I were to dissolve sugar into water, remember those do not dissociate, they do not break apart. So we would have no ions in solution, no charged particles, so there'd be nowhere for that electricity to go. So I'm not sure how much you know about electricity, but electricity is really just the movement of electrons. So if we don't have any charged particles, those electrons don't have anywhere to go, so it just stops. So we would call this type of solution a non-electrolyte. It does not conduct electricity. Okay, and that would be our molecular compounds. Over here on the far right, we see that it does conduct electricity. We would call this an electrolyte. So when our ionic compounds dissolve, they produce many ions in solution, and the electrons can jump from ion to ion, and this solution will conduct that electricity. So it'll come in, jump through the solution, come out, light our light bulb. Okay, so we would call that an electrolyte. Where have you likely heard these terms electrolyte before? Probably on Gatorade or Powerade, right? So when you work out, you sweat. And what comes out of your body when you sweat? Well, ions, right? You salt, so sodium, potassium, magnesium. So if you're working out for long periods of time, really, really hard, you need to replace those ions that you sweated out. So that's where Gatorade is marketed for you to replace those electrolytes, to replace those ions that you sweat out. So sodium, potassium, magnesium are all in that Gatorade drink to replace those ions. They just use this fancy word called electrolyte because it sounds a little bit better than ion, right? Are there also non-electrolytes in that Gatorade? Oh, yeah, right? If you look at a regular bottle of Gatorade, there's lots and lots of sugar in there too. But do they market the non-electrolyte sugar? Well, of course not. No, they don't. That would be no fun. But there's also non-electrolytes in there as well. There's also a lot of sugar dissolved in there. Okay? So that's probably where you've heard electrolyte before. So non-electrolyte does not conduct electricity. That would be our molecular compounds. Electrolyte does conduct electricity. That would be our ionic. Well, I haven't addressed this guy in the middle yet, have I? Right? So what do we notice about this light bulb? We notice that it's lit, right? It does have a little bit of light coming out of it, but it's not nearly as bright as this light bulb. So science, unfortunately, is not black and white, yes or no, electrolyte or non-electrolyte. There's also this kind of gray fading area in the middle. So it's more like a continuum instead of a yes or no. So what this middle picture indicates is there's some solutions that maybe just form a few ions. So some of the ionic compound breaks apart, but some of it stays together. So we've got this guy in the middle too that we need to talk about. Okay. So here's our continuum. Non-electrolyte. It starts over there. Non-electrolyte does not form ions in water. That's going to be our molecular compounds. Strong electrolyte. So that was our really bright light bulb. This is going to be our ionic compounds. And these ionic compounds completely dissociate in water. So every single sodium chloride particle that I put in breaks apart into sodium and chlorine. So every single particle that goes in dissociates, breaks apart. Nothing stays together. Our weak electrolyte does conduct electricity, but just not as well. So we see our dimly lit light bulb. And for a weak electrolyte, that's still going to be an ionic compound. But it's going to be an ionic compound that only dissociates a little bit. It only breaks apart a little bit. Okay? So partial dissociation. So if I put 3 molecules in, maybe 1 breaks apart and 2 stay together. So only a few of them break apart. So there are ions in there for electricity to be conducted. There's just not as many. So it's going to take a little longer or not do it as well. Here's a picture of a weak electrolyte. So just so you can kind of see what's going on. You don't need to know this, but this is acetic acid. So acetic acid is kind of the poster child for weak electrolytes. So what we see here is acetic acid is actually a pretty big molecule. So this is our acetic acid molecule here. So here we see the acetic acid molecule does stay together. And then what we see right here is sometimes it breaks apart. So here is the acetate ion and the hydrogen. Those broke apart. Here's the acetate ion and the hydrogen. Those two broke apart. So every once in a while, one of these molecules will break apart, but a majority of them just stick together. So that's an example of a weak electrolyte. And the way that we depict this in chemistry is with a 2-sided arrow. So up until now, all of our chemical equations have been a 1-sided arrow. So if I drop sodium chloride into water, all of it is going to dissociate into sodium dissolved in water, aqueous, and chlorine dissolved in water, aqueous. Okay, so this is our 1-sided arrow. Everything pushes to the product side. This is our first look at a double-sided arrow. So if you take 152, Chem 2, we'll see lots and lots and lots more of these double-sided arrows. But this is our first indication that some of it goes this way and some of it goes that way. Some of the ions break apart and some of them stick together. So that's how we indicate that it's a weak electrolyte in a chemical formula, in a chemical format. Okay. So that ends our discussion about electrolytes and non-electrolytes. Certainly going to see a couple of these on an exam. Most likely going to be like multiple choice questions. So what kind of compound is this? Would you expect a light bulb to light? Those sorts of things. Hope you guys found this helpful.